Okay, we're in calculus looking at section 4.5, linear approximation and differentials. So when we start looking through, we're going to start looking through at a couple different aspects. So the first thing we're going to look at is the definition of linear approximation right here. So it says, suppose f is differential on an interval I containing the point A. The linear approximation to f at A is the linear function. So we talk about the linear function equals f of a plus f prime of a times x minus a, once again for x in some sort of interval. Okay, so we're going to be looking at, we're going to take that original value here plus the derivative value times x minus a, and this is going to give us a linear approximation for the function. As we continue on, we talk about the linear approximation and concavity. Basically kind of tells us how graphs are flowing in there. The relationship between delta x and delta y. So it says, suppose f is differentiable on an interval I containing the point A. The change in the value of f between the points A and f plus delta x is approximately delta y is approximately f prime of x delta x, where a plus delta x is in the interval. So basically we start talking about if we have some point, then we have some sort of change in x. So as our x numbers change in there, how are they relating back to that change in the y overall? And it's kind of bringing in this derivative here. We come over here to the uses of this. So the uses of linear approximation. To approximate f near x in A, use f of x as approximately a linear approximation, which equals f of a plus f prime of a times the quantity of x minus a. Now, to approximate the change delta y in the dependent variable when x changes from a to a plus whatever that x change is, we're going to use f prime of a times that change then. And so this kind of really starts leading us into how have people in the past been able to approximate irrational numbers. Try to figure out these irrational figures, these very complex problems without having calculators. This is the calculus that was being used in the understanding within here. The next part of this section talks about differentials. Okay, so the definition of a differential is let f be differentiable on an interval containing x. The small change in x is denoted by the differential d of x. The corresponding change in f is approximated by the differential d of y equals f prime of x dx. So what we start seeing here is that they kind of start seeing a little bit of that linear approximation in here for f of x and then f of x plus d of x. So they're saying that the change in the y is going to be dy equals f prime of x dx. So if you think back, we used to have dy over dx equals our derivative. Well, now we're basically just breaking apart those labels within and going to be using it differently for the overall problem. Do realize most of our problems in here do require us to take the derivative and just start using point substitutions in there. So do not overcomplicate this section. One of the little notes I have up here is as we start looking at problems in itself, the approximation delta y is approximately dy improves as dx approaches 0. Okay, so once again, as we start looking at this problem right here, just this little bit, we see that as this derivative starts getting closer and this gap starts getting closer and closer in here, our equation starts becoming closer and more and better, more or better, okay?